I'm going to be talking about the Go memory model. I'm Steve Bezic. I work at Twitter, where for over the last 2 years, I've been working on Periscope and video infrastructure, writing code every day. And before that, I spent many years working at a high-frequency trading firm where I ended up dealing with a Java memory model on a regular basis. If you want to contact me, you can find me at Steve Bezic at Twitter. And so when you hear Go memory model, you might think it refers to something like memory allocation or garbage collection or stuff like that. But what it actually refers to is what sort of guarantees the language gives you when you're accessing shared memory from multiple Go routines. During the presentation, if you have any questions, just raise your hand and I'll do my best to try to answer them. So before we dive into the Go memory model, we need a little bit background of how concurrency works in Go. So Go provides us with a few different concurrency primitives. One is goroutines. You can think of those a little bit like lightweight threads that are managed by the Go runtime. And if you look for the syntax, you just call go and then a function you want to run, and that runs that function concurrently. So in this case, we're going to sort the list, but we're not going to wait for it to finish. We're just going to go on to the next statements. We also have channels, which is a way to safely communicate between different threads. Syntax looks like this. You can create a channel here. We've got a channel of integers of size 10. Then that syntax is how you can send a variable onto that channel. And then below it is how you can receive from that channel and assign the value to V. Oops. So let's just go into an example. Can everyone see the screen okay? Cool. So right here, we are defining two variables, a, which is an int, done, which is a Boolean. And then in main, we call go setup. So we run setup concurrently. It's at a to 42 and then done to true. And then back in main, we busy wait, we check until done is true, and then we print a. So what do we think will happen? Get some hands. Do you guys think it'll print 42? Okay, I'm raising my hand. Does anyone think it might do something differently? Yep. And so if we look at this, yeah, I raised my hand, print 42, that's definitely a possibility, but other things can happen as well. One other possibility is it will never return, or it can also print 0. So you might think, why can this happen? And there's two reasons for this. One is reordering. So your compiler and processor are allowed to reorder instructions. And you might think, why would it do it? It turns out it doesn't run it in the exact order that your program is written. And the reason for this is performance. Basically, yeah, I'll give you an example. This is called loop fission and is a compiler optimization. So in this first case, we are iterating over a loop and setting two arrays, all the elements in A to 1, all the elements in B to 2. The compiler might decide, I can make this run more quickly if I split it up into 2 separate arrays and just constantly work on A and then constantly work on B, and then that'll take advantage of data locality. So the field of compiler optimizations is very large, and there's a lot of different things they can do to kind of speed up your code. And similarly, your processor can also reorder instructions, and it can do this, for example, if it knows you're loading from memory and it's going to take a while, instead of just waiting for something else, waiting for the load to finish, it can go and do some other instructions at that same time. So it'll change the order. Another reason that can explain this is memory visibility. So for this, let's jump into what your system might look like. So here we have a machine with 4 cores on 2 sockets. And so each core has its own set of registers, L1 cache and L2 cache. Then there's a shared L3 cache across the socket, and then all of the processors have access to the RAM. So let's say there is a thread running in core 1 that's updating a variable. It will end up updating it in the registers. Now let's say we have a separate thread running in core 4 and it wants to read the value of that variable. What the value it will get is likely a stale value that may be in its L1 cache or it might be in RAM, but it's not going to be able to go and just immediately read the registers for core 1. You might think, why doesn't every time core update the value of a variable, why doesn't it write it to RAM? And the reason is it would be too slow. And so as you see, as registers are very fast, but they hold a very small amount of data, and as you go down the line, you get bigger and bigger, but also slower and slower. And so from performance-wise, it just isn't possible to make it so that if a different thread is trying to read that same variable, it's going to get the most up-to-date value. So here we get into the Go memory model. And if you, so the Go memory model is pretty short. It's about 6 pages long, and it's very easy to read. I'm going to cover nearly all of it in the presentation tonight, but I'd highly recommend taking a look yourself. And the first line of the memory model document says, it specifies the conditions under which reads of a variable in one Go routine can be guaranteed to observe values produced by writes to the same variable in a different Go routine. The next line they have is, if you must read the rest of this document to understand the behavior of your program, you're being too clever. Don't be clever. And I definitely agree with the idea that you shouldn't be clever, but I kind of feel like this statement kind of does developers a disservice. A lot of times the Go memory model is considered some sort of advanced idea. If you read any articles about concurrency in Go, it seems like it's rarely ever mentioned. And the problem is if you, I think the Go memory model is fundamental. And if you don't read the Go memory model, you are likely to make incorrect assumptions that are going to cause problems in your code. And before I get too far, I just want to say the common saying, don't communicate by sharing memory, share memory by communicating. So in the Go community, this is what people would recommend doing. Over years of experience, determined that it's really hard to properly share memory. It's very error prone. You have to make sure you synchronize it correctly. If you do it wrong, you get deadlocks. And so the creators of Go added channels into the language, and channels make it very easy to communicate between threads and do it in a safe way. So everywhere where you can, you should like to use channels instead of some of the other techniques I might mention here. But I also feel like not all of the different types of problems you're going to solve are going to fit channels very well. So you might have to go through some of these techniques. So the memory model defines that when you're within a single Go routine, the reads and writes will behave as if they're executed in the order specified by the program. Then the compiler is allowed to reorder the instructions as long as it doesn't change the behavior defined in the language specification. But the order observed from one Go routine may differ from the order perceived by another. So let's say one Go routine sets A equals 1, B equals 2. Another Go routine might see B equals 2, and then later see A equals 1. It also defines something known as happens before. Happens before is a partial ordering of operations. If you see it written down, it looks like this. A happens before B with the arrow. Happens before is transitive. And within a single Go routine, the happens before order is the order expressed by the program. This is an important part. To guarantee that a read of a variable observes a write to the same variable, the write must happens before the read. I'll repeat that. To guarantee that a read of a variable observes a write to the same variable, the write must happens before the read. And certain operations create happens before relationships. You may be familiar with locking. You grab a lock, you update a value, you release the lock, a different thread grabs that same lock, reads the value, it's going to have the most up-to-date value. And if there isn't a happens before relationship between two events, then they're said to happen concurrently. So here is where I kind of repeat kind of the most important part of the talk. So whenever more than one thread accesses a given state variable, and one of them might write to it, they all must coordinate their access to it using synchronization. To put it more plainly, you must synchronize the reads as well as the writes. So let's take a look on how this works with an example with two threads and locks. So in thread 1, we set x equals to 1. We lock the lock, we set y equals to 2, and then we unlock the lock. So everything before an unlock, which is visible up there, is visible to everything after a later lock of the same lock. So here we know that z equals y is going to set z equal to 2. Also, notice it says everything before an unlock. It doesn't just say values that are manipulated while a lock is being held. So it's everything before an unlock. So in this example, even though this j equals x happens outside of the lock and the x was changed before the lock was acquired, we know here that j is going to be set to 1. So what creates a happens before relationship? So there's a number of different examples. One is goroutine creation. So yeah, the Go statement that starts a new Go routine happens before the Go routine execution begins. So in this case, we've got the function hello. We say a equals hello world, go f, and then f prints a. And since the statement that starts a no routine happens before the execution begins, a equals hello world happens before printing a, so we're guaranteed to print out hello world. Another thing that creates happens before is channel communication. So a send on a channel happens before the corresponding receive from that channel completes. So here we have a channel of integers of size 10 and a, which is a string again. And so in main, we call f from Go routine. We say a equals hello world, and then we send 0 to the channel. And then back in main, we receive from the channel and then print a. And so that receive from the channel, by the time that completes, that the send happens before that receive. And so the print, the a equals hello world, then transitively happens before printing a. So we know that in this case, we're guaranteed to print hello world again. Similarly, when you are receiving from a channel, you can return from someone sending a value, or if the channel is closed. And so similarly, if you close the channel, the close happens before the receive that notices that's closed. And so in this example, it also prints hello world. This one is a little bit tricky. So there's unbuffered channels in Go, which are more for kind of a handoff. So what happens, well, I'll just go through the example. So you call GoF, which sets hello world, and then receives from the channel. And then in main, you write 0 to the channel. And so for these unbuffered channels, instead of you sending and then continuing on, you send and then wait until someone else comes and receives from that channel. And then the receive happens before the send completes and goes to the next line. So here we know that, okay, before it can continue from sending 0 to C, that receive would have happened, and before the receive was setting hello, a equals hello world, and so printing in this case is going to happen before, or yeah, it's going to guaranteed to print hello world. Then we can also see with the size of a channel. So in this case, yeah, we have a channel of integers of size 3. And so before you're allowed to send the fourth item on the channel, there must have been one received that has happened. And so this example, we've got a slice of work that needs to be done, which is functions. We iterate through it all. For each case, we create a new goroutine. We send one to the channel, do the work, and then receive from the channel. So the first 3 times when they create the goroutine, they're going to successfully send one to the channel. The fourth one, it's going to block because there's no more room on the channel. And then the receive must happens before I can finally put something new in there. And because of this, we can guarantee that no more than 3 W's are running at any given time. Go also provides this functionality called sync.once that makes it safe for you to initialize something from multiple Go routines and have it only happen once. So yeah, you can be guaranteed that the function that's passed into once.do ends up happening before the once.do returns. So in this case, we also have hello world being guaranteed to be printed. And so yeah, what creates the happens before relationship? We saw Go routine creation, channel communication, locks, sync.once, import initialization. So if you import a different package and there's an init in that package that happens before anything in your package runs. And then there are also functions in the sync package. So some examples might be weight groups or atomics. Unfortunately, with Go compared to Java, a lot of things aren't well defined or documented. In Java, many of the libraries will say, okay, this action creates a happens before relationship, which is not the case for Go. And so, for example, with atomics, I had to dig into a GitHub issue where someone was communicating with the maintainer, where the maintainer actually explained what sort of happens before semantics you can expect with atomics. Oops, sorry. So yeah, so we've got this example from the beginning. And so like I was saying, you're only guaranteed to see a write if there's a happens before relationship between them. And so we are reading the value of done, but there is no happens before relationship between writing the done and reading the done. So there's no guarantee that we see the value. And so it could just be false the whole time. Another thing that can cause issues with this is compiler optimization called hoisting, where it can look and determine if there's any code that is part of a loop that doesn't change. It can just calculate that value once and then substitute that value there for each of the times. And with the memory model, there's nothing that's going to force the value of done to change, and the value of done doesn't change during the loop. So it could just replace that done with false. It's also possible that it does see the value of done being set to true and then prints A, but because there's no happens before relationship there, it would just end up printing the 0 value. So this is something you shouldn't do. You shouldn't rely on this behavior. So what should you do instead? You can use a weight group. It's designed specifically for this type of situation where you want to spin up a bunch of tasks to run in Go routines and then wait until they're finished. So yeah, you just call the wait group, you add one, you go do your work, and then you wait. And then as long as each of the Go routines call wait group.done, it'll kind of decrement it. And then once the wait finishes, that creates a happens before relationship. And then you're guaranteed to print A equals 42. No, it's not deterministic. There are 3 different options it can do. And I'll talk a little bit later about kind of what that means. So let's look at this example here. A lot of times you will use Go to write web server software, and you might want to track the success rate of some of your handlers. So you might create something like this, a success rate tracker, which has two fields for success and failure, which are ints. And then you also have a mutex there. And so there are two functions on there. There is record and get success rate. So we might expect record will happen on all sorts of different goroutines as they finish their work. You pass in success or a Boolean, true or false, for success or failure. And so in this case, we lock and then we defer to unlock it at the end. And then yeah, if it's success, we increment success. If it's failure, we increment failure. So then let's also imagine we've got another system where, yeah, every minute we've got some sort of observability system. We just have a go routine on a timer that checks the success rate and sends it out for graphing. And so, yeah, in this, it's pretty simple. You just take the successes divided by the successes and failures. Let's ignore the potential for a divide by zero error. But what do you guys think? Will this work successfully? Any hands? Anyone think it will not work successfully? What? Okay. And yeah, so this does not work successfully. And it's the same reason as before. You need a happens before relationship to guarantee that it sees any of the updates. And so yeah, even though we do lock on recording, which is good, it will prevent us from like an increment being lost, but that doesn't affect anything with getting the success rate. And so yeah, even though it's been running for successes, it might read the value of 0. So what should you do instead? Like I was saying earlier, need to synchronize on the reads and the writes. So we've already got that mutex, so we lock that when we access it and then unlock it afterwards. In this situation, it also could potentially be a good fit for a read-write mutex, which would allow multiple readers at the same time. So let's look at this example. So we've got the singleton class, we've got an instance variable, which is a pointer to a singleton, and then we have a function getInstance, which is designed to be called from multiple goroutines. And so here it checks if instance is nil. If it does, it goes ahead and creates the instance, and then it returns the instance variable. Do you guys think this will work properly? I'm seeing a lot of no's. And you're right, this is definitely not good code. And the problem is, I mean, there are a lot, but with this, so with the singleton, you should only have one singleton. You could have two goroutines. They both run and check, oh, is instance nil? Even without any visibility issues, they could say, oh yeah, instance is nil, and then they both go and create their own version of the singleton and then assign it to instance. So that does not work properly. Oops. Okay, so let's look at this example. So now in getInstance, if instance is nil, instead of just going and creating the singleton, we grab a lock, and then we check again to make sure that instance is still nil. Author might realize, oh, there might be some visibility issues where I might not can see it. But now if I grab the lock and the same lock someone wrote it, then I should be able to see it. So I check if instance is nil again. If so, I create it, and then I return it. Do you guys think this will work properly? Not seeing any answers, yes? So let's see. The answer is no. So with this one, it was really, really tricky to me. I had to spend a long time reading a bunch of different posts to understand what is going on here. Because at first glance, it looks like it should be fine, right? Like, okay, you might not see the value of instance, you might get stale value there, but then, yeah, you're going to grab a lock, so you can't create two of them. What could go wrong? So it's pretty subtle. And so if we look at this, when we create the singleton, it's one line, but it's actually multiple operations. So we say s equals singleton, we assign the fields s.x equals 3, s.y equals 4, and then we say the instance equals the address of s. So I was talking earlier about reordering. So it's possible that this can be reordered so the instance equals the address of s happens right after s is created. And what can happen is you've got multiple goroutines. One goes in here, starts creating it. It says instance equals address of s. And then at that same moment, another goroutine can come by, call get instance. Okay, instance is no longer nil, so I'm going to return the instance. Now I've got my singleton. I want to do an action on it. And then it fails because the singleton is only partially created because of the reordering. So remember earlier it said, don't try to be clever. This is an example. You could spend an hour trying to convince yourself, oh, this will definitely work. I've got all my cases figured out. But then the compiler can just do something you would never have expected and end up breaking your code. So what should you do instead? Well, I kind of touched on the once, the sync.once, but it's specifically made for this scenario. So if you have many goroutines and they need to access the singleton, in each goroutine, just call once.do, create the instance, and now you're guaranteed that it's going to be created and you can access it. So I brought up a lot of things. You might be convinced, okay, there are some theoretical problems that can show up, but this isn't a big deal practically, right? Like this is going to be super rare, probably won't make a difference. Or you might be saying, you know what, like, yeah, I agree, this could be an issue, but in my case, I don't need the exact value. So if it's a little bit stale, that's not a problem for me. So that is not true. So these data races aren't okay. One thing they can lead to is memory corruption. So, so far a lot of these examples are talking about stuff like a Boolean or an integer. You can also fail to see, sorry, question? This one? Sorry, it's slow. The mutex? Yeah, this is just kind of a global mutex, which can be acquired right there. Yes, yeah, it's mutual exclusion, which will, and as long as you're using the same mutex and you aren't copying it, it only allows one goroutine to hold on to it at the same time. So only one goroutine will be running the if instance equals nil. yeah, it's really tricky to see. I'll explain something that'll actually make this a lot easier in a little bit. Yeah, so we're talking about memory corruption. We were dealing with just like primitives like integers. A lot of times you'll also be writing pointers, and the problem is if due to memory visibility issues, you don't see the latest write for a pointer, it could be nil. You try to access it, and then you get a panic because you're dereferencing the nil pointer. Another thing that you will see very often is this fatal error, concurrent map read and map write. So in Go, the standard map is not thread safe. And if you try to read and write without doing proper synchronization, you will end up getting this error. And what's nice about the Go map is that they added this panic as a way to help you. It's a best effort functionality, and you might say, why would a panic be helping me? That causes my program to crash. And the reason for this is it is a lot easier to see what's going on when you get a panic and it tells you exactly where and what went wrong, as opposed to the alternative where your code is running in production for months and just subtly corrupting all of your data. And as another example, people who might say, oh, this is a pretty rare thing, you don't have to worry about this in practice. If you Google for this error message, you will see a lot of people confused why their system, which worked fine in production for months, all of a sudden is crashing all of a sudden when they finally get a lot of traffic. Another reason why these data races aren't okay, mentioning deterministically. And so the thing is, anything with a memory model, multi-threaded or race conditions, it's not deterministic. So you might write some code. If you don't follow the memory model, you could say, oh, it works fine on my machine. It's good to go. But that's not true. Just the fact that it works once doesn't mean that it's going to work later. It's all kind of probabilistic. And yeah, a lot of this stuff is extremely rare. And yeah, you'll be fine now, but it'll cause problems at the worst possible time. So I've worked on some systems. Yeah, it's fine in production for months. There's a really big event. We have tons of people come to our site, most traffic we've ever had, and then all of a sudden we get panics or we get deadlocks. And that's not something you want to happen. You'd much rather have this happen when you're testing your code. And then also at the point when you get a lot of traffic, it's also going to be very hard to debug. Instead of like you just deploy this and then, oh, I immediately know there's an issue, so it must be in this small amount of code I've written. It can be really hard to try to track down, like in the whole code base, what is causing this to happen. Also, the program will break, not now, but when there are compiler upgrades, you upgrade your version of Go, you switch operating systems, you switch processors. So for example, the code base I'm working on right now started in February 2014, which was Go 1.2. We are now on Go 1.11 and have upgraded numerous times. So you might think, oh, it works for now. We kind of really have to get this out. This won't be an issue. Then months or years down the line, there's going to be a new version of the compiler that adds a new optimization, which is something they've been doing a lot recently. And then all of a sudden, your program's going to have all sorts of problems. Similarly, talking about switching processor, so you might have been running x86, and then now you realize, oh, Amazon offers these new ARM EC2 instances. I can run on that. I'll save a lot of money. It turns out ARM is a lot less strict than x86 for all the types of reorderings you're doing. And then all of a sudden, your program just doesn't work at all. So don't try to think, oh, I've got a special case. This will be okay. I don't really need it to be exact. That is not going to work out well for you. So luckily, Go comes with this great built-in tool called the data race detector. And so what it does is you can, when you're running your code, you can just pass the flag race, and it will go and detect any sorts of violations of the Go memory model that you have. It's not static analysis. It instruments your code when it's running, so it ends up making it take up to 10x more memory and run 20x slower. But it's super, super useful because it gives you amazing error messages. So I ran it on the first example I gave in the talk, and it tells you, oh, there's a data race. So it's a read of this address by the main Go routine, which happens on line 15. There's not a happens before between that read and the previous write, which happened on line 7. And so when this happens, you can go in and immediately figure out what's going on. Because of the performance issues I mentioned earlier, I wouldn't recommend running this in production, but where this works really well is in a continuous integration environment. If you have some integration tests and they might have multiple Go routines and exercise your code, just add this in here, and then it'll make it very easy to detect any sort of regression regarding the memory model. I guess when you go home or the next day you're into work, I highly recommend running this on some of your own code, and you're very likely to learn something about what's going on. So conclusion, communication between goroutines requires a happens before relationship. If you don't do that, you could be bit by reordering and memory visibility issues. Both threads, reading and writing, must participate. Don't try to be clever. You aren't going to be able to outsmart the compiler or outsmart the processor, and data races aren't okay. So resources, I really recommend checking out the Go memory model, 6 pages. Everyone should take a look. Yeah, it's basically a lot of my slides map one-to-one with what the memory model says. There's this amazing book called Java Concurrency in Practice. You might say, why am I talking about a Java book? But the Java memory model is very similar to the Go memory model, and I haven't seen a better coverage of the subject of concurrency or memory models. So I highly recommend checking that out. There's also on the Go wiki, there's a section for Learn Concurrency, which links to lots of different presentations or blog posts about how to learn concurrency. And finally, there's a great talk by Brian Mills at GopherCon 2018 called Rethinking Classical Concurrency Patterns. And this is a kind of much higher level discussion of concurrency than I did tonight. It talks about what sort of problems you might encounter trying to use concurrency to solve issues, and what sort of high level constructs and patterns you can use to solve them. Oops. So let's have some questions. Okay.
My name is Fode. Thank you for the great talk. I know that Twitter moved from Ruby on Rails to Scala a couple of years ago. How does Go fit in your backend right now architecture?
Yeah, so the question, I guess it was on the microphone, so we already know it. But yeah, how does Go fit into the Twitter architecture? So I work on Periscope, which was a Twitter acquisition from a few years ago. And so at the time of acquisition, their code was all written in Go on AWS and continues to be. So it's continued to work very well. And we're kind of doing some initial experiments with everything else in Twitter is typically written in Scala, and do some initial experiments to see if Go also helps with some of the other situations. Okay, I'll just give this to you.
Again, pardon, I'm not the developer here, but if the locking it has to bring the routines back down to RAM, does it optimize it differently, or is it always a performance hit because you're trying to reach back down into that memory?
So you mentioned, does locking have to bring it down to RAM? I don't think that's fully accurate. What goes on behind the scenes is very tricky. There's these kind of cache coherency protocols that kind of can transfer, like for example, let's say you're both on the same core. You don't have to go all the way to RAM. There's other levels that are earlier that are shared between them. So, and you mentioned performance. Yeah, so the actual ways it ends up being implemented, a lot of times you will, it'll add some memory fences to the code to just tell the processor, okay, it can't reorder certain operations. Performance-wise, my understanding is if it's not contentious with a lock, only one person ends up trying to grab it, it's not much of a performance hit. But if there is a lot of contention around the lock, then it ends up needs some arbitration and ends up taking much longer. But for all of this, like we saw some of the examples for the singleton where someone tried to be clever, do some double check locking to avoid grabbing the lock. The real answer is implement it correctly, benchmark, see if this is a problem, and then only then try to optimize it. question. All right.
So you mentioned it's super helpful to add the dash race, like during a CI environment. We actually have that whenever we run Go test. Super helpful. It's got a lot of things. But you mentioned that it works by instrumenting the code. Does that mean that if I'm doing it on Go test and I don't have a test that covers like a specific function that has like a race condition in it, will it not tell me about it?
Yeah, so what GoTest does is it's only going to mention the race conditions that it observes where, okay, there was a write here and a read here. So yeah, if you don't have a test around a part of code, it won't detect that. It's not a static analyzer. Another thing I forgot to mention is that for the data race detector, it's not that well documented, but if you look at the blog of the person who created it, he says that the data race detector is guaranteed to report any races that it sees when it's executing. So it will guarantee to display that, which is very, very helpful. Oops.
At the beginning of your talk, you mentioned sort of the canonical advice around shared memory access, like communication to share data across Go routines. But then I think you also mentioned that there are scenarios where you might not want to do that. So, and I was wondering, I think that in your talk, you talked upon like a common one is like singleton initialization. I was wondering if you were like initially referring to like other times when it's easier to like work around that.
Yeah, so in terms of kind of using channels, yeah, there are many other times when that channels aren't a good fit for the problem you're trying to solve. For example, let's just say you have some sort of kind of metrics or something you want to deal with some counters that get incremented across multiple Go routines. One way you can solve this is, okay, every time instead of just incrementing it, they send a message on a channel. You've got another Go routine whose whole job is kind of serialize all of these. It reads it and then increments its own store. You can do a lot of stuff around there. Or you could just use an atomic and just increment it that way, and it's a lot easier to understand and less error prone. So yeah, there's many different, I can't really come up with a list of many different scenarios, but there are lots of cases where channels don't fit that well.
What's the easiest way to simulate a volatile Java keyword in Go? Is it with atomic or something else?
Yeah, so when I was just thinking between the differences between the Java memory model and the Go memory model, this is kind of one of the bigger ones that stands out. And as far as I know, there is no real way to kind of reproduce this kind of functionality that volatile gives you in Java. Yep.
So more of a Java programmer here. So in Java, I don't think you can create a lot of threads because there are some like memory issues with that. But in Go, I heard Go routines, you can create thousands of them. So why is that?
Yep, that was on some of the, I had to cut down this presentation because I had previously given it for an hour long. I was going to explain kind of what the differences are. And yeah, Go routines are much cheaper than something like Java threads. There's a number of reasons. One is the stack size. With Java, I think the default stack size is something like 1 megabyte or 2 megabytes. In Go, I think it's on the order of 2 kilobytes or 4 kilobytes. And you might think, why doesn't Java just set to 2 kilobytes or something like that? And the reason for this, I mean, this is a whole nother talk, but I'll just give you the short version, is Go makes it so that their stack size can be changed over time instead of fixed. So you can start out with very tiny stack and then grow it as necessary. Other reasons, in Java, when you create a thread, it ends up creating like a POSIX thread, an actual one hardware thread, as opposed to Go, which uses this M of N scheduler to kind of multiplex multiple Go routines onto different threads. So you don't need a one-to-one relationship there. And finally, Go does some things that make context switches a lot cheaper than otherwise would be. Any more questions? Oh, cool. Yeah, and afterwards you can reach out to me if you have any questions.